to Litma Laboratory. My name is Nick Litma and I belong to the Department of Advanced Materials Science. Our laboratory works on oxide materials and specifically nanoscale oxide materials. Oxides are of course well known to everybody, and perhaps the most famous oxides are jewels, like this big sapphire crystal that I'm showing to you now. But in microelectronics, which is of course everywhere today in computers, your phones, that electronic systems are based on field effect transistors that also require oxides. For example, hafnium, aluminum, silicon oxides used as gate insulators. And this type of practical applications of oxides require thin films. And our laboratory specializes on the fabrication, the growth, and the analysis of oxide thin films. In front of me, you can see a vacuum system, which is called a pulsed laser deposition system, which we use to grow nanoscale oxide thin films. Now, oxides are well known to be very stable materials that are difficult to evaporate and difficult to grow in thin film form. We therefore use this powerful pulsed laser behind me, and if I start this laser, you will hear kind of a clicking sound when the laser is firing. And you can see bluish light coming from the laser on this white paper. When I put the black piece of paper into the focus point of this laser, you can see plasma coming from the paper. These flashes of light are very high temperature gases formed in the evaporation process, and the sound is just like the sound of lightning strike. We do this evaporation, of course, inside the vacuum chamber, and that way we can evaporate and grow these very thin oxide materials on a scale of single atomic layers or single unit cell layers. And this is a very useful technique then for characterizing the properties of these materials, especially when we go down to the nanoscale. We don't study bulk materials. We look at two-dimensional, very thin layers, one-dimensional nanowires, nanodots, nanopillars, nanopyramids, and other shapes where the physical properties of the materials are defined not only by the structure of the crystal, but also by the shape of the crystal. And this is an area where all our students work on. Our students have a chance to learn how to use these vacuum systems, and then they take these thin films, which they have made themselves, and they will use various characterization tools to measure their properties. For example, they may use X-ray photoelectron spectroscopy, transport analysis, various scanning probe microscopes like scanning tunneling, scanning atomic force microscopes, and so on. We are working on a number of different projects depending on the interests of the students. Many students these days want to work on renewable energy sources, and especially on methods of harvesting solar energy and generating chemical fuels. We therefore work on photocatalytic materials, which are oxides that collect sunlight, and when they do that in water, they can generate hydrogen gas that can power cars, buses, or the chemical industry. Other people are more interested in specific physical properties of materials, for example, looking at interesting electronic states in strong spin orbit systems like iridium oxides, which exhibit, for example, Weyl semimetal states, or they may be looking at very high-speed spintronic applications and developing antiferromagnetic or ferrimagnetic oxide thin films for these purposes. So students who come to this laboratory have a chance to choose their research topic, and as long as it's related to thin films and oxides, we can develop an interesting research project which combines materials synthesis, materials characterization, and possible applications. So I welcome all of you to Litma Laboratory, and I'm sure you can enjoy your 2 or 3 years in the laboratory doing challenging research and getting excellent results. Thank you.